So you can see the question: a plane wave is incident normally on a perfect conductor as shown in the figure, where EXI and HYI and PI are the electric field, magnetic field and the Poynting vector respectively for the incident wave. The reflected wave should have, you have four options. Okay, you have to find the condition for the reflected wave or the reflected wave components. Okay, so in order to solve this particular question, you have to apply the boundary condition. Okay, so suppose this is the boundary. Okay, and this side you have conductor, the perfect conductor, so sigma is basically infinite. Now you can see the incident wave has a electric field component as EIX and the magnetic field component HYI, and the power PI is going in Z direction. Okay, it's PI, because electric field in the X direction, the magnetic field in the Y direction, so X to Y is basically representing the Z direction, so the power is flowing in the Z direction. Okay, now let us first consider the electric field only. Okay, so you can see, as electric field is in the X direction and this electromagnetic wave falling normally, the plane wave is normally incident normally. So as it is normally incident, so this X component of the electric field is basically tangential to this interface. Okay, so this EIX, this component basically tangential to the interface. Now what we know, that the tangential component of the electric field is continuous across the boundary. Okay, but we also know the fields inside this ideal conductor is 0, right? Now in order to satisfy this boundary condition, when this particular electric field will come to this position, that is just across this interface, okay, there will be a self-generated electric field which will cancel this particular incident electric field in order to maintain this boundary condition, that is the electric field is continuous across the boundary. So the reflected electric field ER X directed, okay, this is ERX identical to EXI with a negative sign. Okay, so this condition basically comes from the boundary condition. In order to satisfy that condition, that the electric tangential component of the electric field has to be continuous across the boundary. Okay, so you can see option A is correct. Okay, you can see ER of X equals to minus of EI of X. Okay, now let us consider the magnetic field component. The magnetic field component is Y oriented, so let us assume this is Y direction. So EIY, sorry, E not, it will be H, the magnetic field. Okay, so HIY, this is basically the magnetic field component, and you can see this particular magnetic field component is also tangential to the boundary. Okay, so we have to apply the boundary condition of this magnetic field, tangential component of the magnetic field. Now what we know, the tangential component of the magnetic field is continuous across the boundary if there is no surface current, but if there is a surface current, it will be balanced by this surface current. Okay, so this particular magnetic field when come to this interface, okay, this HIY, it will produce some surface current. Okay, it will produce some surface current across the boundary. It will produce some surface current across the boundary. Okay, so what will happen, this surface current again produce some electric field in the same direction. Okay, and that will create your reflected wave. So if I draw this particular boundary some other way, you can see, suppose this is the boundary. Okay, now this is the tangential component of the magnetic field H of YI. Okay, H of YI, this is the tangential component of the magnetic field, and this is the tangential component of the electric field, okay, and the power is going in this direction, okay. So this tangential component of the magnetic field producing some surface current, okay, and that will again produce some electric field, okay. Now we have already seen that this is the magnetic electric field E of reflected electric field E of R x, and the surface current will produce some magnetic field, okay, in the same direction. So this is basically H of y r, okay, and you can see that H of y r is basically equals to H of y I, okay. There is no negative sign because the direction of both the reflected magnetic field and the incident magnetic field is same, okay. And considering this perfect conductor, so there is no loss due to the surface current flow, so the deflected magnetic field has the same magnitude of this incident magnetic field, okay. So they are directly equals, no negative sign, right? So option B is not correct. You can see option B is not correct. Now what is the power flow, the direction of reflected power flow? You can see, you can apply the right hand rule, that is E cross H is basically give you the direction of power flow, okay. E to H will give you the direction of power flow. This is basically opposite to the incident wave. So from that sense option C is also correct, okay, because this power is flowing, the reflected power is flowing exactly opposite direction to the incident power flow. So PR is basically negative of PI, okay. So option C is also correct. And what is option D? It is given as ER of x equals to EI of x. No, it is I have already shown you that option E is correct, option A is correct, so option D is not correct, okay. Thank you.